We've now talked about acids and bases, what they are, how to name them, how to calculate H plus and OH minus. We're going to foray into a few other little things here. The first is a new definition for an acid. Why do we need a new definition for acids and bases? It turns out that not everything that acts like a base follows the definition of gives off OH minus in solution very clearly. And the same thing for the other one. And so we're going to come up with another definition. It's a more general definition, works really well for lots of different cases, not just those cases where we easily give off OH minus in solution. The primary example of that is ammonia. Ammonia is a base. But if we say that something gives off OH minus in solution, ammonia has no oxygen in it, so it can't actually give off OH minus in solution. And so how can this one act as a base? Well, it turns out what it does is if you take ammonia and you let it sit in water, it'll actually steal a hydrogen ion from the water, becoming NH4+, which we call ammonium, and leaving behind OH minus. So if you're not very strict about your definitions, it did kind of produce OH minus, and so it kind of fits in that first definition, which we call the Lewis definition. But maybe we need another definition that's a little more flexible and can talk about how ammonia is a base here instead of, even though it can't directly produce OH minus. And so Bronsted and Lowry came up with their own definition, and they said that this is an acid is a proton donor, and a base is a proton acceptor. And why are we all of a sudden talking about protons here? Well, remember, what is an H plus? H has one electron. You take it away, all that's left is its proton. And so it's just H plus. H plus donor, H plus acceptor. And so what happened here? Ammonia took an H plus from water and accepted that proton, which makes ammonia the base. Water gave away that proton, which makes water the acid. Now, this definition also works for the very simple ones. If we had our HCl plus H2O, actually, forming H3O plus Cl minus, then that works just fine too. We've got HCl donating, giving away an H plus. It's a proton donor, makes it the acid. And we've got water accepting that, right? It accepts it and becomes H3O plus and makes that the base. And so we have the acid and the base. So this definition works not only for the simple cases, but also for cases that are slightly more complicated, like ammonia, giving us a little more flexibility in how we define things. So most people, when they talk about acids and bases, they actually use the Bronsted-Lowry definition, and they say an acid is an H plus donor or proton donor, and a base is an H plus or proton acceptor. But here's a funny thing. If I write the same equation I wrote on the last one, HCl plus H2O becomes H3O plus and Cl minus. I've got HCl as my acid, right? It gave away H plus. I've got H2O as my base. It took H plus. What I'm going to do is I'm just going to take this exact same equation. I'm just going to write it backwards. I'm going to write the products as the reactants and the reactants as the products. So I'm going to write H3O plus Cl minus goes to HCl plus H2O. So nothing exciting, just took the same thing I had up front and wrote it backwards. Now, we can also interpret this one in terms of acid and base chemistry. If there's H plus flying around, which there is, here H3O plus becomes H2O by doing what? By giving away H plus, right? He had an H plus, and he gave it away. H3 went to H2. A plus sign went to no charge, so we gave away H plus. That makes this an acid. What did Cl minus do? He accepted the H plus, which makes him the base according to our Bronsted-Lowry definition. So now we've got H3O plus is our acid and Cl minus is our base. But that's very interesting, because if we look at the beginning, HCl was an acid. But if we wrote the reaction backwards, Cl minus is the base. So HCl is the acid, but then Cl minus becomes a base. The easiest way to think about this is if you think about the proton as just something you can give back and forth. So here in one hand, I've got the proton, which means I'm an acid because I could give away that proton. Here, you want a proton? I could give away that to somebody else, like, say, my other hand. My other hand, what is he? He's a base because he could take that proton, right? I want that proton, I want that proton. Ah, I took it. But now, what happened? The roles are reversed. This hand now has a proton in it, and so it has it to give away, which makes this hand now an acid. And this hand over here has nothing, which makes it now a base. But I could go, ooh, 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 and take it. And now this hand is the acid, even though it was just a base. And that's what happens to the reactions too. As an acid-base reaction runs, the thing that was an acid, once it acts like an acid, it gives away H+, which means it's now eligible to take H+. And so the thing that was our acid in our products is now our base. How do we write that? I'm going to rewrite this equation here just so we have room for things. So here we have that same equation. We decided that HCl was our acid. We decided that H2O was our base. So what do we call H3O plus? Well, water, at first water here, didn't have the H, then it took it and became H3O plus, which means it's now an acid. So we're going to call this guy an acid. But how do we distinguish this acid from this acid if we call them both acid? And how we distinguish them is by using the word conjugate. Now, conjugate acids and bases, I tell you, it took me like 30 years to really understand what those were. When I finally understood what those were, I was like, duh, I can't believe this took me like 30 years to figure out. But it did. So if it doesn't quite make sense at first, don't worry. You got about 30 more years. And in that time, they'll even give you a PhD in chemistry, even if you really don't quite understand what these words mean. Conjugate acid. When do we use the word conjugate? We use the conjugate when we're talking about products. Anything on the right is a conjugate. Anything on the left is regular. Reactants are acids and bases. Products are conjugate acids and conjugate bases. And it's just about this passing game. Who has the H plus now? If you have the H plus now, you're the acid. Whether you're a reactant or a product, if you have the H plus, you're an acid. The only time is, if you're a product and you have this, then we use the word conjugate. If you're not, then we don't use the word conjugate. So what is Cl minus? Well, we know it's a conjugate because it's a product. But what is it? It's a Cl minus. He has no H plus anymore, right? He wants that, he wants that, he wants that. If he wants it, if he's willing to accept it, that makes him a base. And just like we saw before, the thing that was the acid becomes the conjugate base. The thing that was the base becomes the conjugate acid, because as soon as they react, that hydrogen moves over and they switch roles. So we have to be able to identify acids, bases, conjugate bases. But just remember, conjugates are always products. They're just a way, it's a word to distinguish between reactants and products. And the reaction's just always as written. Reactants are on the left, products are on the right. So I could take the same reaction and write it backwards. In fact, let's go ahead and do that. Let's write H3O plus aqueous plus Cl minus aqueous goes to HCl aqueous plus H2O liquid. Now what do I have? I've got an H3O at the plus. It gives away an H plus, and so I call that the acid. And then HCl, Cl minus takes that, and so he's the base. But now, right, the Cl minus is here. He takes the H. Now what is he? He's HCl, but he's an acid now, so we're going to call him an acid. But we're going to call him a conjugate because he's a product, just the way we wrote it. It literally is a function of just the way you write the equation. Whatever's on the left is the reactants, whatever's on the right is the products. Water is therefore the conjugate base. Why? Because in this scenario, the H3O plus had the acid, right? And as soon as the H3O plus gave it away, he's more the base now because he could accept that back and become H3O plus. So H3O plus is not an acid or a conjugate acid. Don't memorize that a chemical is an acid or a conjugate acid. In fact, you can't even memorize that it's an acid. 99% of the time you'll be right. But there's times when you can't even know that, because sometimes water acts as an acid, sometimes water acts as a base. There's chemicals that do that. So what we really have to remember, reactants are always acids or bases. Products are always conjugates. So HCl in my first one was just the acid. HCl in my second one was the conjugate acid. The conjugate just depends on whether you're on the left or on the right. Were you a reactant or a product? Products get the conjugate label. So be able to identify those in chemical reactions by looking at it and looking where that proton's moving around. Here's a question, and you might not be able to do this one just by pausing and thinking about it, so we'll go over it together. What's the conjugate base to HClO2? And you're like, well, you just talked about these conjugates and things like that, but you had whole reactions written out. You didn't just have a chemical. Well, HClO2 is going to be my reactant here. I'm going to react it with water. Okay. Now, why did I react it with water? Because that's what we always have around in acid-base reactions. So I'm going to take that guy and react him with water. What's going to happen? Well, in order for something to have a conjugate base, so I've got a conjugate base over here that I'm looking for. What has to be on the opposite side, right? It has to be that this guy acts like an acid. An acid is always paired with a conjugate base because the acid has the H+, it gives it away, and what's left is a base now. Which means water's the base, which means it's going to be accepting a proton. And so we know water becomes H3O+, because it's accepting a proton, because that's what bases do. Where did it get it? It got it from this guy, and we end up with ClO2-. So my answer for this one is ClO2-. Well, that's kind of a complicated way, and there's some really tricky logic going around that can really mess with your brain if you try to do those just by thinking about it. So here's a shorthand for talking about conjugate acids and conjugate bases. If someone just asks you what's the conjugate base to something, what is a base, right? A base is something that takes hydrogen. It gets rid of hydrogen. And so the easiest thing to do is when you say what's the conjugate base is you take off a hydrogen. So if I say, hey, what's the conjugate base to HNO3, you're going to take off an H+. What happens when you take off an H+? You end up with NO3-. That charge is important. You need to have that charge there in order to balance out the charges. All right, how about if I had H2SO4 and I asked what's my conjugate base? I'm going to take off an H+, and I get HSO4-. And some people think, well, you know, Professor Clements, if you take the H's off, don't you get HSO or don't you get SO4-2-? And the answer is no, because conjugate is always the transfer of one hydrogen, not 2 or 3 or 4. And so H2SO4, you subtract one hydrogen, and when we say, what's the conjugate base of H2SO4? The answer is HSO4-. How about conjugate acid? What if I say, what's the conjugate acid of ClO4-? What's the conjugate acid of ClO4-? Well, when I wanted conjugate base, I got rid of an H, right? If I want conjugate acid, I'm going to make it a little more acidic by adding an H. and I get HClO4. Right? So I add an H plus, I should say. Right? So I balance out that, I get HClO4. What does that look like in a reaction? ClO4 minus plus H2O becomes something. Right? So if this guy, if I'm finding the conjugate acid, means this guy needs to act like a base, right? Because that's how they're always paired. A base has a conjugate acid, an acid has a conjugate base, which means this guy's the acid. If water's an acid, he's giving away H plus, and it's going to become OH minus, and that ClO4 is going to take that H plus and look like that. So that's how we can do it using a reaction. But the easiest way, if you're saying what's the conjugate acid, make it more acidic by giving it a hydrogen. If you're saying what's the conjugate base, make it less acidic, more basic, by taking away a hydrogen. The tricky ones are when you have something like H2PO4, which has a minus sign, and I say, what is the conjugate base to H2PO4 minus? And that one's a little harder because you're like, well, I could add a hydrogen, get H3PO4, which I know is phosphoric acid, or I could take away a hydrogen and have HPO4 minus, but I don't know. But again, if I'm asking for the conjugate base, I'm going to make it more basic by taking away hydrogen minus H plus, and we get HPO4 minus. Got to balance that charge there. If we took away an H plus, we made it more negative. And so we have HPO4 minus as the conjugate base of H2PO4. If I asked for the conjugate acid, I would have added an H plus and gotten H3PO4, or phosphoric acid. But for conjugate base, I take away an H. So just be aware of that. People use that language, and I will ask you those kind of questions as well. So what's the conjugate acid to HPO3 minus? Take a moment. Think about that and figure it out. Acid, you want to make that more acidic, so you're going to add an H plus. Adding an H is going to give us something with H2, and so it's got to be that one, even if we don't know the rest of it. Why is it not H3? Because conjugates are always one hydrogen, not two or three. So H2PO3 minus, we balance that, right? We had a minus 2, we added a plus 1. And we got a minus 1 at the end, right? So minus 2 plus 1 is minus 1. Okay, so those are our conjugates. Now, I love this picture. What do you see in that picture? Most people notice the strong man at first, and they see the weak man on one side. And you know, what you see in the mirror is not always what's reality, but my favorite part of this one is down here, is what the cat sees. And in the mirror, the cat sees a lion. So this weak guy sees somebody strong in the mirror. The strong people see somebody weak in the mirror. And so what we're going to talk about next is the strength of acids and bases. And it turns out that there are some things in the world called strong acids. What is a strong acid? It is an acid that dissociates 100% into ions in water. An example of that is hydrochloric acid. Dissolves 100% into H plus and Cl minus. You might remember this from our strong electrolytes and weak electrolytes. A strong electrolyte dissolved completely into ions as well. The only difference with a strong acid is one of the ions is H plus. So HCl is a strong acid, dissociates completely 100% in water. We generally draw just the single direction arrow to say, hey, this is going all the way that direction. But if we've got a strong acid, guess what we probably also have? We have weak acids. What is a weak acid? It's an acid that partially dissociates. Into ions in water. Okay, so what does that look like? Well, our favorite weak acid, I talked about this in the chapter on electrolytes, is hydrofluoric acid, and the only reason people use that is because it's easy to write. HF is a weak acid. And when you put that into water, mostly, absolutely nothing happens. Mostly HF just floats around as HF because it's really happy that way. But a small fraction of them will actually dissociate into H plus and F minus. And you get that reaction here. Notice now I'm using the double arrow to indicate that both of these are present, that the reaction doesn't go all the way to one side, and if we make all H plus and F minus, we've got both present. We have mostly HF and a small amount of H plus and F minus. And that is a weak acid. And as you might expect, kind of like we had a weak electrolytes, weak acids, there's not many ions present, but there are some. How do we know if something's a strong acid or a weak acid? Turns out it's pretty easy because there are only 6 strong acids. And every other acid in the world is weak. What are the 6 strong acids? There are halogen buddies, HCl, HBr, and HI. Notice who's not on that list is fluorine. HF, hydrofluoric acid, is not a strong acid. Nitric acid, sulfuric acid, and perchloric acid. Those are the 6 strong acids. All other acids are weak. So if we're doing an assignment or a problem or something, we run across this acid we've never seen before, you can make the assumption that it's a weak acid because these are the only strong acids. There are some texts and some sites out there you'll see on the internet that list H3PO4, phosphoric acid, on the list of strong acids. The textbook we're using doesn't, so I'm going to stick with that, but you might see that. It's kind of on the edge of strong and not strong. So those are the 6 strong acids. Now, why did I have that picture of the strong man and the weak man? Well, because it turns out if you take something like a strong acid, so let's use HBr just for something slightly different, you got HBr goes into H plus and Br minus. Okay, looks like that. Remember, we draw this right-hand arrow to say it kind of goes completely in this direction, forming 100% H plus in Br minus. So we have HBr over here. He's all together, but then we break it apart, and we've got H plus all by itself over here, and the Br minus is left without the H plus. Now, what do we know? If we're looking at Br minus, we know this is our conjugate base, because it can now accept that hydrogen. It makes it its base, right? This guy's acting as an acid. Okay, so if we have that conjugate base, what we want to know is how good of a conjugate base is it. We know this guy is strong because he's on our list of strong acids. HBr is a strong acid, but what kind of conjugate base is Br minus? Well, what we want to know in that case is how likely is Br minus to accept an H plus. So Br minus is floating around here. How likely is it to accept an H plus and hold on to it? And we have to think, well, if it did, if we made HBr, what would happen to that HBr? We know that HBr would immediately dissociate and form H plus and Br minus because that's what HBr does because it's a strong acid. So Br minus, even if it got the H, would give it right back. That's not a very good H acceptor if you take it and you give it back, right? The Indian giving is what they call it when you have gifts, right? Is you give them back. And so Br minus is not a very good base, and so we call this a weak conjugate base. So a strong acid is paired with a weak conjugate base. On the other hand, if we have a weak acid, so if we have, say, acetic acid, HC2H3O2 is a weak acid. It's aqueous. We draw the double arrow to represent that both things are present. We get some dissociation at H plus and C2H3O2 minus aqueous. But most of it stays as acetic acid. So what kind of conjugate base is C2H3O2? Well, acetic acid is this guy, and occasionally he'll be like, if I have to, I'll give away my H plus to someone, but I don't really want to. I'd much rather have it. And so if he does give it away and he's floating around a solution and an H plus floats by him, what's he going to do? Ooh, he's going to grab onto that thing. He's going to say, I want that H plus. That C2H3O2 minus is very good at grabbing onto H plus and holding onto it. And so we call this a strong conjugate base. Now, it's a little more subtle than that, but in this class we're just going to do strong and weak, weak and strong. So a weak acid ends up with a strong conjugate base. A strong acid ends up with a weak conjugate base. And so they're always coming in pairs, the cat and the lion. When one's weak, the other's strong. Because if you're really good at giving away H+, you're not going to be very good at taking it back. If you're really good, at holding on to H+, you're not going to be very good at giving it back. And so there is our strong and our weak. All right, we're going to stop there, and we're going to do buffers as our last video.